Hello. We've talked about genetic drift as being a mechanism of evolution that is really based on sampling error. So genetic drift is only going to take place when a population is small. So as an analogy, what I thought I would do is to prepare a simulation using, instead of the population itself, a coin. And so the coin is going to be flipped, and it will either be a head or a tail. So we can think about the head being one allele and the tail being the other allele. So since our coin is fair, equal chance of a head or a tail, then we can say that the allele frequencies are the same, or the equivalent are the same. So here's what I've done. I've set up a simulation in R, which is open source software. It's becoming very popular for lots of statistical analysis. What I've done is set up 4 different files. In one of the files, I'm going to flip my coin 10 times, and I'm going to do it 5,000 times. So we're going to do it a whole bunch of times. And then I'm also going to run the same simulation, but this time I'm going to sample 20 coins. I'm going to flip the coin 20 times. I'm also going to do it 100 times, and finally 1,000 times. What I'm going to do at the end of this video is to go through the code if it's something that you think you might be interested in. But for now, we'll just move through pretty quickly. So in this simulation, we're letting a 0 be heads and a 1 be tails. So if we flip our coin a whole bunch of times, we would figure half would be heads and half would be tails, and so the average value we should get should be 0.5. So here's a loop that I've set up to run the simulation for sampling the coin 10 times, but what we're going to do is do it 5,000 different simulations. So here we go. We'll run the code itself. And now I have my file, 5,000 means in it. And what I'm going to do is to look at a histogram of that. And what you can see is that, lo and behold, the most common outcome is 0.5, which indicates 50% heads, 50% tails. But I still got an appreciable number of 4 heads and 6 tails, or 6 tails and 4 heads. And then continuing on, so I even got some instances where I got all tails or I got all heads. So it can happen with small coin flips when you do it a whole number of times, that sampling error can end up producing values that are very different than what we expect. We expect 0.5, a mixture of equal number of heads and tails, but just by luck, we can end up with 9 heads, 9 tails, even 10 heads or 10 tails. Now what I'm going to do is to do the other 4 simulations as well. If I do the other simulations, then the x-axis is going to change according to the values that are found for the simulation. So what I really want to do to be able to compare these 4 simulations is to use the same x-axis. So what I'm going to do is to run a whole bunch of code, and we'll look at the output here. So we'll run this. And it will zoom in on this. You can see now. So here's the 5,000 simulations where I just flipped the coin 10 times. Here I flipped the coin 20 times. Here 100 times. And here 1,000 times. And you'll notice that the x-axis is the same for all 3. And what's clearly the case is that when the number of coin flips is small, I get a whole lot of more variability in my outcomes. So again, thinking if we've got P equals Q equals 0.5, then just by sampling 10, I could end up with a new population where P equals 0.1 and Q equals 0.10, or even P equals 0 and Q equals 1. So that's certainly possible, happens not infrequently, getting 8 or 9 coin flips with just flipping 10 altogether. If I go to 20, then I end up with a little tighter distribution, so I still get some outliers. So I've got 16 or so, 16 or 17 heads or tails here. Looks like 15 or 16 heads there. But the modal number is at 0.5. And the reason the blanks are here is because when I have small numbers, I have only so many possibilities. I get 0.5, 0.55, 0.6, and so forth. Now it gets a little more interesting when we go down to higher numbers of coin flips. So if I flip the coin 100 times, and again I simulated this 5,000 times, so this histogram represents the results of 5,000 simulations of 100 coin flips, you can see that the distribution has become much more narrow. I get fewer of these really odd outliers. I might get something on the order of, it looks like maybe 60, 65 tails and 35 heads, but that's about as far as it goes. And again, I'm always getting, the modal number is right at 0.5. And if I flip 1,000 times, then my distribution becomes very tight, and looks like maybe about the most unequal distribution I get is maybe something on the order of 460 heads and 540 tails or something like that. So the point is that when we have a small sample, that we can get divergent values from the population we started with. But if we have a large sample, then we are pretty much going to mimic what the population looked like. So I had my coin that was fair, so I know that I had an equal number of heads and tails in my population, and I could flip that coin as often as I wanted. If I do it 1,000 times, then I see that that's a pretty good representation of the population at large of my two possible outcomes, heads and tails. We're going to see the same thing happening with genetic drift, that genetic drift is only going to be taking place when we have small populations, when we can get these sometimes strongly divergent proportions of P and Q, or heads and tails. What I'm going to do now is to go back to the code if you're interested in seeing what I did to get to the diagram that I showed you. What I did first was just to set up 4 different files, and each of them is going to have 5,000 entries into it. Each entry is going to be the mean of however many coin flips I did. So here we have 5,000 means of 10 coin flips, of 20 coin flips, 100 coin flips, and 1,000 coin flips. What I did here was to set up a file which has the 2 possible outcomes. So let 0 be heads and tails be 1. So these are combined. And then I just set up what's called a for loop. So what I'm going to allow I to do is to vary from 1 to 5,000. And it's going to be iterated 5,000 times. So what I'm going to do is to create a temporary variable called samp, and I'm asking R to sample the coin, sample either take one of these two, 0 or 1 randomly, and I want to do it 10 times, and I'm telling it to replace. So once it draws a 0 out, then the 0 goes back in, so it's possible to draw 10 zeros, in other words. So this loop is going to continue to cycle. Every time it goes through, I is going to increase by 1, and once I get to 5,000, then it's going to stop, and I'll have my file, which will be filled in. Then here, what I did was just to tell R to give me a histogram of sample 10, and we can just run that real fast. Oops. And so there it was. Then I did the same thing for the sample 20 file that I wanted to set up. So it's, again, similar to the one above. I just changed this to 20 instead of 10. So I'm flipping the coin 20 times for each simulation. Here I'm flipping the coin 100 times, and here 5,000 times. So what I wanted to do was to put all the data in a single, all the histograms into a single frame. And what I did was to combine all of the 4 files that I created, the 4 simulations, into what I called a combined data set called a data frame. So I just put those 4 together. Then what I need to do to print that is to put them all into a single column. So that's what I did. I had what I call stacked data. So I just used this particular subroutine called tidyr or reshape to put the 4 columns of data into one column identified as either a 10, 20, 100, or 1,000 coin flip simulation. And then I just use this graphing package called ggplot, called Grammar of Graphics is what the GG stands for. And what I did was just to say I want histograms. I want you to fill in with cornflower blue, which is a nice looking color to me, and I want you to wrap them together so that we get a 2x2 design. And then that created this graph, but then to print the graph to the screen, I simply need to call it. So I call comb graph or combine graph. So when I run the whole thing, let's go back up here to the very beginning where I set up coin. Actually, I set up here. And we'll just click run, and it will run through all of those commands, and then I get my final result here, and I can zoom in, and there I see the very broad distribution of outcomes for a 10 coin flip simulation, a little more reduced for 20 flips, less variation yet for 100 flips, and then with 1,000 flips I get a very, very tight distribution. So that's just a quick look at how the simulation was set up in R. R is becoming a very popular programming language. A lot of people are using it for statistics. I use it in my own research. And if you take any of my classes in the future, you will likely be using R as well.